So today I'm going to talk about going from these sort of older ancient ideas that sort of arose in the context of the ancient Greek philosophers to how we get to something closer to where we are today and understanding our place in the universe. So let me remind you that while this is a cosmology class, we've been talking primarily about some things that might seem pretty basic, like is the Earth round, does the Earth go around the sun, and that kind of thing. But keep in mind that while today when we think about cosmology, we of course think about the entire universe, which goes well beyond our solar system and what the planets are doing. For these people living long ago, effectively that was the universe, right? I mean, to some people, the Earth was the universe. And the planets and what they were doing with respect to the Earth and the sun effectively represented the entirety of the universe. And the notion of what the stars were was something that really wasn't that well understood at all, especially in these times that I'm talking about, going back to something like the year 100 or 150, which is where we left off last time with Ptolemy. And so what we're going to do today is kind of start off with this picture of the universe that Ptolemy had put together where we were last time. Let me remind you of where this came from. So this is all built upon the ideas of Aristotle. So fundamentally, Aristotle is the authority here. Aristotle said, look, the Earth is round, it's a sphere, the Earth doesn't move, it doesn't turn, it sits fixed, and all of these other things that we see in the sky, everything around us that looks like it's whizzing around us, in fact, is doing just that. We're not spinning or moving. These things are all orbiting around us in effectively constant circles, or something like circles, over the course of the day and months. What Ptolemy had to do was change Aristotle's most basic idea that the Earth was fixed and everything went around us on circles and modify it a little bit. The reason why he had to modify it is he had really, really accurate data tables, especially for the time, and what he showed was that the motions of the planets in the sky do things that just don't make sense in the context of a theory where everything is going around the Earth in constant circles. So what he did is he basically modified Aristotle's model. He kept to the basic idea that the Earth is at the center and things can only move on circles. But what he did is he added kind of multiple circles, and these are called epicycles. And so the idea, for example, is that Mercury is going around the Earth, but it's going around the Earth in sort of a funny way, where there's a circle going around the Earth, and about that circle, there's another little loop going around, and that's what Mercury sits on. So with respect to us, it's basically doing a loop-de-loop around us. And that had to be the case with basically all of the planets. The moon doesn't have to do that in his model. And of course, we know now today that the moon doesn't do that. It just goes around us. So this picture, this kind of weird, when we look at this kind of picture, it looks kind of crazy to us. This was a really successful model. In fact, it was the dominant model of what the universe was like for about 1,300 years or even more throughout most of the world. And so what I'm going to do now is use this as kind of a starting point and move forward and sort of track the trajectory of people trying to figure out whether or not this is right. Now, another thing to keep in mind is that the Ptolemaic model was really, really powerful and successful because it got things right. Okay? This model, the one that he produced, did really, really well. So if you were interested in predicting like when eclipses were going to happen, or where the planets were in the sky on the day of a particular battle, okay? If you were interested in astrology, the Ptolemaic catalog and the Ptolemaic system worked really well. So his model worked, and fundamentally that's why it lasted so long, is because it worked so well. The question of whether or not it actually represented reality of the universe is something that some people thought about and some people didn't think about. So the trajectory I'm going to talk about is one in time, but I wanted to give you just sort of a sense of the global outlook of this. The picture here, and the one I want to sort of impress upon you, it'll be much more evident later in the course, is that this idea of figuring out our place in the universe, where we are, how we're traveling through it, how big the universe is, et cetera, is really a global endeavor. Okay? People from all over the world, reaching far back in time, contributed to this in sort of complicated ways. And especially today, advances in science and cosmology and astronomy rely a lot on sort of global efforts in technology, importantly, but also just generally intellectually. There's a lot of good ideas and they flow back and forth. So in particular, the things I picked out are, now here's where Ptolemy was living at the time. He was living in Alexandria. He was Greek, but it was controlled by Rome at the time. I will discuss, there's a long tradition of Indian astronomers, and I will discuss one fundamentally because his work and the work of sort of the people who followed him in India influenced significantly Central Asian astronomers who themselves influenced people closer to the Middle East. And this was and scholars living in the Middle East, in particular in Baghdad, were really important scribes and thinkers who eventually would allow people in Europe to read the works not only of the thinkers in the Middle East and effectively even in India, but they also transcribed the works of the Greeks. And so most of the work from the ancient Greeks that was being read by people in Europe during the Renaissance were translations done in the Middle East. And so this sort of the ability for knowledge and ideas to be transported across the globe, it's a pretty complicated thing. And of course, it's taking a long, long time, if you look at the dates here. So let me just start here. Let me start in Baghdad with this particular person, Alhazen, in the year 1000, roughly in the year 1000. There were a number of really, really impressive thinkers who were living in this part of the world between the 9th and 12th centuries. It's not obvious to me that most people know this, but Baghdad was arguably the most vibrant metropolitan, cosmopolitan city in the world during this time. In particular, there was a famous library there that became known in Europe as the House of Wisdom, where a lot of scholars were supported to do fundamental work, where they transcribed texts. They did a lot of work on developing the Hindu-Arabic number system that we all use today, so how we write numbers in base 10 with zeros, et cetera, et cetera. A lot of that was developed there. This guy in particular, Alhazen, was nicknamed the physicist in medieval Europe. The medieval scholars in Europe who eventually were able to read this guy's work were fundamentally impressed, and he really influenced the way people thought. In particular, he wrote a really important treatise on optics. So that's how light travels through glass and how we understand light. He understood how the eye worked really well. He was, as far as we know, the first person to understand why rainbows are rainbows, why light going through raindrops creates rainbows in the sky, stuff like that. His work directly influenced Leonardo da Vinci, Galileo, Kepler, and many, many others. For our story, one of the things that's very important is that he studied very carefully the model of Ptolemy and compared that to other data that were being collected by observatories in this part of the world, and demonstrated that Ptolemy's model was not self-consistent. So if you imagined that there were these crystalline spheres that were carrying all these planets around in these crazy orbits, he showed that that was not self-consistent, that they would just constantly be crashing into each other. Getting the moon right was really hard. And so what he basically did is said, look, there's something fundamentally wrong with this. And he worked on trying to make it better. He was unsuccessful. He didn't publish a model that sort of got everything right, but he was pretty critical of the model. And people living at this time understood that this Ptolemaic system, whether or not you like it aesthetically, there was something fundamentally wrong with it. And they understood that. Let me pick out another person living roughly at the same time, but now in closer to Central Asia and the area of sort of modern-day Afghanistan. And this is Al-Biruni. So he is considered one of the greatest scholars of all time. Some people say he was the greatest thinker between Aristotle and the European Enlightenment, or you might then give it to Newton or someone like that. Let me just give you a few of the things that he was doing. He was another one of these polymaths, right, who sort of did everything. He figured out a new way to measure the size of the Earth. You're going to be doing a rocket mix module on how the ancient Greeks figured out how to basically figure out how big the Earth was. But he developed an even more sort of subtle and really smart way of figuring how big the Earth was. And he concluded that the Earth was so big that there's probably another continent between this side of Europe and this side of Asia. Right? People knew that there were oceans on either side. But he basically proclaimed that there's almost certainly a continent in between those two oceans, or the same ocean, they didn't know, right? And he said it would be reasonable to suspect that there are people living in that continent because it would be really big, and sort of speculated like that, right? So some people argue that he actually discovered America without ever leaving his, where he was. He wrote a lot of influential works in history, physics, mathematics, astronomy, linguistics, comparative religion. So he compared the religions in India to those in the Middle East in a sort of really kind of sophisticated way. He was extremely critical of Aristotle. So he wrote something like 150 books. Only a very small fraction of them actually survive to today. But there's a lot of records of him having sort of arguments with other scholars in this part of Central Asia about why everyone was sort of a disciple of Aristotle, but he was constantly attacking Aristotle and saying, look, he said this is wrong, this doesn't make any sense. And so he was sort of this sort of free-thinking individual. One of the things that he did that really influenced the way he thought is he actually traveled to India and spent, I think, at least a decade there, I can't remember. But he spent a long time in India talking to scholars there about how they saw the world. And that influenced to think about whether or not the Earth could be spinning. And he made a pretty strong statement that it was impossible to tell whether or not it was spinning. He said, look, there are some people who believe that it spins. And he said, given the data we have, we can't know the difference right now. And he talked about the kind of data that would be required in order to determine whether or not we are spinning or not. So again, this flies in the face of what Aristotle was teaching, the Ptolemaic picture of what the universe was like, etc. One of the great Indian astronomers that influenced the writing of Al-Biruni was living some 500 years before him. And we don't know that much about exactly, not that much survives of everything that Aryabhata wrote. But we do know he was a very influential mathematician, astronomer living somewhere in northern India. He, for example, understood that the moon and planets were shining because they reflected the light of the sun. So this was something he made a pretty strong case for. He taught that the Earth does spin. So he didn't say we can't tell whether or not it spins. He says the Earth spins. In his cosmology, the Earth was spinning. And that explained why the stars went up and down over the course of a day. So you would see the stars repeat themselves up in the sky, looping around every day. It's not because they're spinning around us, it's because the Earth is spinning. He had kind of a funny picture of what the solar system was for us, though, because he had the Earth spinning, but he still had the Earth at the center of the universe. He had the moon and the sun and the planets going around the Earth. But he had the Earth spinning. And this idea that the Earth is spinning, again, is something that influenced these Central Asian thinkers. And those ideas would eventually percolate into Europe, where it's hard to believe they didn't influence Copernicus and other people at the time. One of the things that was very clear, though, throughout this period is that there were signs that the Ptolemaic system had problems. Now, as I mentioned, there were a lot of people who just didn't care whether or not it represented reality. What they cared was the Ptolemaic system gave them more or less the right answer. Okay, because they thought that positions of where the planets were in the sky told them something about whether or not they should fight a battle or, they believed wholeheartedly in astrology. Interestingly enough, a lot of these people, like Al-Biruni and others, were employed to be astrologers. And what they would do is you could tell by their writings that they thought this was all bunk. They thought astrology was complete bunk. But the people who were employing them as astrologers didn't understand that because they didn't even really read what they wrote. So they would be like, oh yeah, you should go have your battle now. And then they'd go back and study the more serious studies. But fundamentally, there were cracks. People knew, so people who thought hard about what the observations were saying knew that there was something funny with the Ptolemaic picture. But exactly what to do about it was something that was a little shaky. I just wanted to add one thing to this. Here are these stars that I had before about when these things were happening, and now I'm going to move on and start talking about effectively what's called the Copernican Revolution that happened in Europe around the year 1550 or so. But something very, very important happened in China sort of around the same time that Ptolemy was living, and that's paper was invented. Now, prior to the proliferation of paper and eventually the development of the printing press much later, passing knowledge along was a difficult thing. And effectively, a lot of the strides were made in these great centers of learning. Like there was a great center of learning in Alexandria, there was this great center of learning in Baghdad, and there were only sort of very special places where you could actually get information. In order to get a copy of Ptolemy's work, right, someone had to actually copy it by hand on papyrus or something. And then you had to bring it somewhere. And there were all kinds of errors in the copies, and it was sort of a messed up situation. And that delayed progress. Now, as soon as you had paper is a lot cheaper to make than these other kinds of writing materials. And paper really was a very important technological advancement that allowed a lot of these sort of intellectual advancements to then occur. And so, if you just sort of look and see, eventually, because of some wars between, empires here and here, eventually a paper would spread from China to Baghdad, and people were making paper in Baghdad around the year 800 AD. And that's about the time when this sort of intellectual flowering started to happen as well. I'm not saying it was the cause, but it certainly helped. And then eventually, over time, paper made it to Morocco around the year 1000, and then eventually back up to sort of Central Europe. It was pretty common in Central Europe around the year 1400. Not too long after that, Copernicus was born. And during this time, too, the printing press had been developed, and then books were really starting to be made available. So the big figure here is Nicholas Copernicus. Copernicus was a Polish priest. He was born in the year 1473. He was one of the very first scholars to have his own private library, right? He didn't have to go to one of these great centers like the Library of Alexandria or the House of Wisdom in Baghdad. He didn't need sort of effectively a king's power. He didn't need an emperor to endow the existence of a library and employ all of these people to sort of keep records in a library, who would then, hire scholars, etc., right? It was possible at this point, if you were, you were more well off than most people, but it was popular for sort of like, it was possible for someone like Copernicus to have his own private library. He would have copies of these important texts from Greek philosophers and others. He knew from all of his reading that the Ptolemaic predictions were inaccurate. Okay? He knew they actually didn't give the right answer. So this, was fuel for him to say, well, maybe something else is going on. He also thought that Ptolemy's model was just ugly. And he's quoted as saying that it was too ugly to reflect the divine work of the best and greatest artist. So he had this idea that there was some, that God basically would have never built a universe like this, with these whirligigs and the roundabouts and everything. It just seemed ugly. And so he had this idea that it must be simpler than this. So what he proposed was a heliocentric model where the sun sat at the center and all the planets went around the sun, including the Earth. Built into this was the idea that the Earth, of course, had to spin on its axis to explain everything we see. Now, he wanted the sun to be at the center from a place in which it can light up everything. And the planets on concentric spheres orbiting in circles around this lantern of the universe. So keep in mind, this is the universe to him. Now, as we discussed already, I'll talk about again, this could easily account for the retrograde motion of the planets. This is why Ptolemy built these epicycles into his model. That every now and then the planets would go forward with respect to the stars, but zigzag backwards and go forward again. As we mentioned, and I'll remind you, this model could explain that retrograde motion just as well as Ptolemy's could. Now, the problem is, it wasn't better than Ptolemy's model. It also had problems. And he knew it. He knew that when he put this model together, it didn't really work. It really didn't work better than Ptolemy's model. It didn't really work worse, arguably, but it wasn't better. And he worked and worked on it and really could not make it better. And that's probably one of the reasons why he waited until basically the year he died to publish it. He died the same year that the book, or his ideas on the revolutions of the celestial spheres, was published in 1543. He died that year. Now, eventually, these ideas would change the world. This would be, one of the most important books in the history of science. It really changed the way people thought. But it took a long time to really catch on. I mean, for example, Martin Luther called him a fool for reversing the entire science of astronomy. So he was not universally revered by everybody when this thing came out. Let me remind you, are any questions about that? Okay, let me remind you that it does get the retrograde motion of the planets correctly. So every now and again, for example, if this is Mars and this is the Earth will overtake Mars in its orbit around the sun, and the line of sight view of Mars with respect to the background stars will shift backwards and forward. And so, in basically equally well as Ptolemy's epicycles gave us the zigzag, this kind of configuration gave him the zigzag as well. So he dies in 1543, and this idea is out there, and some people like it and some people don't. You can't say it's better than Ptolemy's model because it actually it isn't better. It doesn't predict anything better. So at this point, it's just sort of subjective. So people fight about it. There's a story that I'm going to sort of digress on, but it's an interesting story that revolves, it involves a guy named Tycho Brahe. Who's heard of Tycho? Who has not heard of Tycho? Interesting. Okay. So let's good. So you have some time. We have some time to talk about him then. All right. Crazy story. This guy's a very interesting character. Okay. So in 1572, Tycho, who is sort of he's Danish and he's sort of a minor lord. He's reasonably wealthy, not super wealthy, but comfortable. He goes out for a walk with a couple of his servants. And he's an interesting character. So for example, he's this big guy, and he's got a metallic nose. He's got a piece of metal for a nose. The reason why is that he lost his nose in a sword fight, in a duel, with a guy, a younger person in college he had a duel with about who the best mathematician was. So he thought he was the best mathematician. This other guy thought so they had a duel about it, and he lost his nose. So the rest of his life, was just missing a nose, and he wore this false metal piece on his face for that. So they give you a sense of the kind of guy he was. He's going to have a fight because someone said he was better at math than him. So anyway, he walks out, and he was, by the way, a really good astronomer. He was interested in astronomy. He knew the stars in the sky like the back of his hand. So he'd go out and he'd be like, yeah, that star, yep. He's one of these people who's into that stuff. He walks out, and there above his head is a star he's never seen before. This is not supposed to happen. Aristotle said, the heavens are unchanging. They're perfect, and they've always been that way. Nothing new can happen up there. But suddenly, in the sky, this night, Tycho sees a new star that he's never seen before. He thinks he's seeing things. He calls over his servants who came with him and says, "What? Do you see that?" And they're like, "Yeah." Tycho's like, wow. He knew this was a big deal. It was a very, very big deal. Now we know what he saw was a supernovae. Every now and then, it's a pretty rare thing, a star in our galaxy will blow up. And when it blows up, it gets way, way, way brighter than it was before. And we can see things we could never see before. So the deal was, in reality, there was a star there that Tycho could not see because it was too far away. But the star blew up and got super bright, and suddenly he could see it. The long-held belief that the unchanging perfection of the heavens was incorrect, if this was true. If what he was seeing was true, this meant, the rock of Aristotle that all of this stuff is supposed to be built on is starting to crumble, because this is clearly different than what Aristotle was preaching. So Tycho realizes this is important, and he actually begins to work really hard to convince himself and convince the world that this wasn't some kind of atmospheric thing. Okay? Every now and then things would change up in the sky, right? Like shooting stars. Right? So Aristotle saw shooting stars, people see shooting stars all the time. What Aristotle said shooting stars were things in the atmosphere. The Earth's atmosphere can change, and so local things can change. And in fact, shooting stars are things in the atmosphere. So that's consistent. So what Tycho did is he said, look, if this is in the atmosphere, then I should be able to see parallax to it. Remember this idea of parallax, that if something's nearby and I look at it from here, and then I go really far away and I look at the same thing, I'll have to turn my head to look at it. He said, look, if this thing, by the way, this thing stayed up in the sky for a couple months, so it was up there and up there and up there. So what he did is he made very careful measurements of where it was in the sky relative to background stars to see at different places in Europe to see whether or not it would shift, and he sees no evidence that it shifts. So he effectively proves this thing is way outside the Earth. So today we call this thing Tycho supernovae. And effectively with this discovery, Aristotle's idea of the immutability of the heavens was completely shattered. By the way, if you go into the sky today and you take a picture of that region of the sky where Tycho saw his supernovae, it faded. It was brighter than the planet Venus for a few days. It eventually faded out, so we couldn't see it anymore. Today, if you look in that part of the sky, you can take pictures like this. What happened is that star blew up, and then over the course of a few hundred years, its gas that it blew up with has been puffed out. It's now no longer as bright, but we can see stuff emanating from that point where it's been basically expanding since that time. So what happened with Tycho is he becomes super famous. He's kind of a gregarious guy, sort of big personality anyway, and he becomes famous throughout Europe for discovering this new star, this changing thing in the sky. All right? His king, Frederick II, wanted to keep him in his home country. He didn't want him going off to Europe and spending time in France or whatever with all the bigwigs. He wanted him to stay and be famous for him. And he said, look, if you stay with me for the glory or whatever, I will build you the greatest observatory in the world. And he did. It's called Uraniborg, or it was called Uraniborg, the Castle of the Heavens. And he built it on an island and basically gave Tycho dominion over this island, made him sort of the king of the island. And this thing, it's a space between Denmark and Sweden. And he had this thing with like, it was basically run like a small city, and Tycho ran it. Okay, it had really sophisticated instruments to make measurements of the sky. Now, the telescope wasn't invented yet, but they had all of these mechanical devices to help him measure alignments between one star and another, and devices that look like this, called a quadrant. And he had all of this sophisticated stuff, and because he had basically this great resource, he was able to then begin making observations of the heavens that were unprecedented. They blew away anything that were in Ptolemy's tables. They were just the best that could possibly be done. So because he lucked out and discovered this supernova, he now was the most famous and powerful observational astronomer the world had ever seen, because he's bankrolled by this king. And so that's what he did. He just started making observations of the heavens. By the way, he didn't like Copernicus's idea. He thought, look, there's no way the Earth is moving, because if the Earth was moving, I could see the parallax of the stars. I, Tycho, the greatest observational astronomer the world has ever seen, could measure the parallax of the stars, and I don't see it. So he built some kind of crazy model where the Earth was still, and the sun went around the Earth, but then everything else went around the sun. So he had this kind of double model. It's kind of weird. You could look it up. It's sort of this kind of crazy model. Now you look at it and you're like, wow, but that was a very serious thing that he tried to do. So around the same time, he's pretty well known in intellectual circles. He's got this observatory that he's running. Everybody knows he's got the best data. Around that time, a younger astronomer named Kepler, Johannes Kepler, was this young, gifted mathematician. Really, really good, really good mathematician. In fact, a better mathematician than Tycho, but they didn't get in a fight about it or anything. It was pretty obvious eventually. He was totally a Copernican. He thought Copernicus was onto something. He liked this idea, and he wanted to see if he could figure out a way to make it work, to make it better than Ptolemy's picture. And he was confident enough to think he could do it, but what he needed was better data. The data that he could get his hands on wasn't that good. He wanted to get his hands on Tycho's data. So he wrote to Tycho and he said, look, you're awesome, you're so cool. Will you let me work with you? Let me be your assistant. Tycho knew that Kepler was a great mathematician, and he figured he could use him in his island. Or at least he could use him to help develop his theories, etc. I think actually by this time he had lost his island. That's another story. He took him on as an assistant. But the thing is, he actually kept most of his data secret, because he wanted to do it himself. Like, he didn't want to give, he didn't want to give Kepler a chance to sort of scoop him or become more famous than him, right? So what he did is he's like, oh yeah, Kepler, come up, work on Mars. Turns out Mars was the hardest one. Mars was like, no one can get Mars right. Really hard to get Mars right. He's like, yeah, you can have all the data for Mars, And so Kepler started working on Mars. And then Tycho's plan was like, I'm going to figure everything else out and leave him the hard part with Mars. But it turns out he died. He died pretty soon after Kepler came on board. And the story of how he died is also a crazy story. So the story goes, and this is not verified, but the story goes that he went to this party with the king. And the etiquette was you never left the table until the king left the table. And he's there just drinking beer all night with the king, and his bladder burst, and he died from this. So that's the story anyway. So a larger-than-life fellow dies that way, sort of a crazy way, and Kepler gets all the data. He becomes the heir apparent to this great treasure trove of data. So he's working on this, and he just can't make it work. Like, things just aren't working out with his, Copernican picture where everything's going in circles around the sun. What is up? Finally, the light bulb goes on. And what he says is, well, maybe the orbits are not circles. Maybe they're in different shape. His idea fundamentally was that they don't travel in circles. They travel in something called an ellipse. Who's ever heard of ellipse? Hopefully most people have heard of ellipse. Yeah, so it's sort of like a squash circle. It seems simple, right? But people were so kind of caught up in this idea of perfect circles and the perfect shape of a circle that it was hard for them to drop. But because Kepler had the mathematical sophistication to deal with ellipses, to deal with things that weren't simple circles, he was able to apply that to the data, and suddenly everything locked into place and stuff started working out. Now, so instead of circles, he has the planets going around the sun in these flattened circles and these ellipses, and things start working better now than Ptolemy's model ever had. Now let me do a quick aside on this. The history of the fascination with circles and spheres in these pictures goes back to the ancient Greeks. So Plato really was into spheres, this perfect shape. And there was this idea that the heavens would then be composed of these perfect shapes like circles and spheres. And it just makes sense that that's how things would be designed. But the ancient Greek mathematicians also studied other shapes just because of their mathematical beauty. Specifically, they had invented the idea of an ellipse thousands of years, well, about 2,000 years before Kepler. So people had known about the mathematical construct of ellipses, which end up being the things that govern the motion of the planets. They had known about this idea for a long time. They had invented it because it was sort of mathematically beautiful. Now the way the Greeks thought about it was in terms of something called conic sections. So the idea is you have a cone like this. If you have a plane that intersects that cone in a line that's parallel, then you get a circle. But if you tilt the plane, you intersect the cone in an ellipse. And you can describe the shape of that ellipse mathematically. And if you tilt the plane vertically, by the way, then you get something that's something else. Does anyone know what that's called? Yeah, parabola. So when you have an ellipse, you can define it by having this axis, the minor axis, the short axis, and the long axis. Here, if you have a major axis and the minor axis are the same, you have a circle. But if you have a major axis, minor axis that are different, you have an ellipse. So it's sort of in a generalized circle. The way you define it, it's more common for sort of these days for us to define an ellipse because we tend to think about things algebraically, is this way. An ellipse has two foci, or a focus here and a focus here. And if you measure the distance between the ellipse circle from this focus to that focus and add those two up, that number is always the same. That's kind of a complicated way of saying it, but the way to see it is this. So if you have a string, okay, and you tack down the edges of that string on a paper, and you put your pencil on the string and draw a thing around it, you draw an ellipse. Probably, maybe you remember doing this like, 3 years ago when you were all young. To me, it's like the same. I'm so old now. I'm like, I don't remember ever. But probably you did this when you were in grade school or something. I don't know. Okay, you remember this? Is this jogging the memory? Okay. No? Really? You're like me. You can't remember it. You really don't remember ever seeing this?
I've never done that in my life.
Really? Has anyone ever done this? No? I'm just old. Maybe back in the day, right before computers and back when there were dinosaurs walking the earth, this is what they used to have us do in class. All right. Well, anyway, you should all do this now. Go get some thumbtacks, get some string. Okay. The point is, right, that this shape had existed, right? Mathematicians had come up with a reason to think about this thing called an ellipse a long time ago, just because it was mathematically interesting and beautiful. Kepler came along and demonstrated that this idea, this sort of abstract, maybe people would argue useless idea of an ellipse, was actually the thing that governed the motions of the planets in the solar system. They followed this ellipse. And what you will see and what we've found in the history of science, it's amazing how often mathematicians will develop something just because it's mathematically beautiful and interesting. And we will discover later on that those ideas can be applied directly to observations in nature to explain how the universe works. It's kind of amazing. So what Kepler showed was that if you put the sun at one of the foci of the ellipse, the other one is sort of there for bookkeeping purposes, the planets travel around the sun. Planets travel around the sun on ellipses, with the sun sitting at one of the foci of that ellipse. Now, not every single ellipse has the same ellipticity. Some are closer to circles than others, but they're all described by ellipses. Are there any questions about that? He also developed 3 laws of described planetary motion that I'm going to talk about next time. Sort of 3 laws to describe how they move in these ellipses, but it's pretty incredible. All right, so this was 1610. In this very same year that Kepler published these ideas, there was a fellow living 500 miles to the south in Italy, Galileo. He had heard about this idea that there's something called a telescope. Let me, yeah, sorry, I broke this up, so let me move it to this one. So he had got wind of a new device that had been developed up north called a telescope, where people put lenses together in such a configuration that they could see things that were farther away that they could not otherwise see. The people who had developed this idea were using it so that they could spot trading ships as they came in on the horizon first, and therefore be ready at the dock to buy their goods. Galileo said, oh, I can build one of those. I'm smart. So he built his own telescope, and instead of pointing it this way or pointing at his neighbor's bedroom window, he pointed it up. Okay? And when he pointed it up, he saw things that no human being had ever seen before. Okay? Prior to Galileo, every single astronomer, okay, from Tycho to Ptolemy to people living thousands of years before him, had looked up at the night sky and basically seen the same sky. Galileo was the first person to point his telescope up and see things that nobody had ever seen. And with all of this new information, it just changed everything. Now, his telescope was only about a 10 to 30 power telescope. You could buy something, you can go to Target now and go to the toy department and buy something like this. Right? But because no one had ever seen it before, it was amazing. Okay? He saw new stars that had never been seen before. He saw structure on the moon. He saw that Jupiter had moons of its own. There are things orbiting Jupiter. So if there are things orbiting Jupiter, why does everything have to orbit the Earth? Okay? The fact that he saw this structure on the moon demonstrated clearly that everything in the heavens weren't perfect. Now, he did one final experiment that basically killed the Ptolemaic model for good. Okay? And I'm going to walk you through that right now, and we're done. What he did is he was looking at Venus. Now, in the Ptolemaic model, Venus travels around the Earth very close to the sun. Its epicycle stays near the sun. It has to because it had been known for a very long time that every time you see Venus in the night sky, it's always pretty near where the sun just set. Okay? Venus is always near the sun. If it's midnight and someone points up at the sky and tells you they see Venus, this is not Venus. Something else. Okay? Venus is near the sun. And so in the model where you have epicycles, you always have Venus in between, you have Venus going around like this inside the sun. What that means is that Venus will always be lit up as a crescent. So it's only getting sideline sight from the sun. You're about to do your phases of the moon module, and this will all sink in more when you do that. You've thought more about the phases of the moon, why the moon has phases. But basically, because Venus is sort of in between the Earth and the sun and how it orbits, it's never being fully lit up by the sun. It's only being lit up partially by the sun in this model. So with this, now the problem is nobody could have ever tested this before, because with your naked eye, Venus just looks like a dot. But with his telescope, he can reveal structure. So he's going to look for this. He's going to look to see, does it always stay a crescent? Because in the Copernican model, Venus goes all the way around the sun. And the Earth is here. So sometimes we see it fully lit up by the sun. Sometimes we don't see it lit up by the sun at all. So it goes through phases just like the moon. Okay? So the point is, we've got two competing models. They make very different predictions. Copernicus says the moon ought to go through phases. Ptolemy says Copernicus says Venus ought to go through phases. Ptolemy says no, Venus is always a crescent. Galileo has a tool to see what happens. So he looks, this is what he sees. And this is gone. Okay? So unless you're completely irrational and you don't believe what you see, you can no longer believe Ptolemy. It just doesn't work. But this idea lives to fight another day. So this idea, this is the very last slide. So this idea that we have a heliocentric theory is fundamentally new, right? The Earth moves. It moves. The stars are very, very, very far away because of parallax. The universe is much bigger than anyone imagined it was before. Aristotle was wrong. The old ideas are not always right. Just because you had smart people living a long time ago who wrote stuff down doesn't mean it's right. That's a big deal. People are still dealing with that. People are capable of figuring out how the universe works, even if it defies common sense. Okay, have a good weekend.